Good evening, everyone. Welcome to Mapping the Future of Tallgrass Prairie Landscapes. This evening, we're going to hear from two people who are using technology tools that allow them to see things that we haven't been able to see before, or to see things in ways we haven't been able to see before. This program is presented by the Mariana Kistler Beach Museum of Art and is part of a series of programs we've been doing since 2013 under the heading of Prairie Studies Initiative. So programs that sort of seek information from people who have different kinds of expertise in different fields of knowledge and bring them together in conversations to help us better understand this region and the prairie ecosystem that it represents. So this program is actually the result of conversations that the museum has been having with K-State's ITS, Internet Technology Services, and also the new Sunderland Innovation Lab. So we're really excited about the opportunities these partnerships provide for us to really see some of the new visual technology tools that are available for research. Today's speakers are Professor Zak Ratajczak and museum designer and technology lead Luke Dempsey. And I'm going to invite them to introduce themselves before we look at the work they'd like to share with us. Luke, would you like to go first with a short intro of yourself?
Sure. Thanks for joining us tonight, folks. I'm an exhibition designer and at the Mariana Kistler Beach Museum of Art here at K-State. Well, down the road, I'm in my home office right now. My focus is mainly on digital and print graphics, display, design and engineering, and 3D modeling. And as a technology lead, I develop technology-based displays. I advise on and deploy software and hardware systems at the museum and support any of the technology needs throughout the museum. And that is a wide range of things. I'm also really passionate about communicating information effectively, especially as designer of museum information, exhibition information. So I like to explore different ways to do that through technology and unique uses of visual tools so that we can better understand data and the like.
Thank you. Zak, you want to introduce yourself?
Thank you. Yeah, I'd love to. My name is Zak Ratajczak. I'm an assistant professor in the Division of Biology here at K-State. I have a background in mostly biology and a bit of technology. And a lot of my research focuses on a concept called resilience, which we define as the ability to absorb changing pressures without breaking or undergoing a large change in your overall state. So whether that's biodiversity or how well ecosystems function. So my lab group, we use a mix of data tools, on-the-ground measurements, and computer simulations to try and determine what systems are more resilient and what kind of pressures might undermine the resilience of grassland ecosystems.
Great, thank you very much. So Zak and Luke are going to each take a few minutes to share a little bit of their work and their images with us, and then we'll have some time for discussion. I just want to note that if you click on the Q&A on the bottom of the screen at any point, you can type in questions, and my colleague Jennifer Harlan or I will make sure that our speakers get those questions. And if you would like to use closed captioning, just click on the CC icon on the bottom of the page. So take it away, Zak.
Great. All right. So I'm going to click right here to acknowledgements. Just want to acknowledge the members of my lab, the graduate students in my lab who have contributed to this work I'm about to show you, as well as the K-State Agricultural Research Station and National Science Foundation. So all this work is underpinned by these people and the people who have kept the Konza Prairie biological station running for over 3 decades now. So Tallgrass Prairie, it's our home ecosystem here in the Flint Hills. It's a really diverse ecosystem, and it's an ecosystem that's under threat. We only have about 4% of it remaining. And in that remaining 4%, 2 of the major drivers of how this system changes are large animals and fire. So plains bison, once numbered in the tens of millions across the Great Plains, before we're being reduced to a number of 600, and now we have around 30,000 of them today. So although they've recovered, they've still seen a massive reduction in their populations. So I'm going to be talking to you a little bit today about how reintroducing these large animals affects this ecosystem. Similarly, this is an ecosystem that used to burn a lot, both through a combination of lightning strikes and Native Americans purposely lighting fires. And so the best records we have suggest that these grasslands probably burned about every 3 to 4 years. Today, though, about 50% of them burn about every year. About 10% of them burn every 2 years. 24% of them burn every 4 to 10 years. And about 33% of our remaining tallgrass prairie in this region burns even less often. So every 10 years or perhaps almost never. So the question I'm going to show you with some data work today is how do bison impact the resilience to these changing fire regimes we see throughout the Flint Hills region of tallgrass prairie. So the traditional way we study a lot of things in ecology is the quadrat or the transect. So we need to go out and measure differences in vegetation or some biodiversity across perhaps differences in fire. And one of the best ways we found to do that is to set out a series of plots, measure what plants we find there and their relative abundance. And then we use statistical techniques to scale that up to a larger scale or compare different fire frequencies for whether or not we think there's a meaningful difference due to things like changes in fire or grazing. So for instance, where I do a lot of my work, Kanza Prairie, there's a network of 600 of these plots that's measured every year for changes in vegetation, including plant biodiversity. So this is kind of our bread and butter as ecologists, is measuring things with techniques like plots and transects. A really cool innovation that's happened in the last couple of decades and that we've recently gained access to is a set of high resolution data that's provided by planes that fly over our site at a low altitude. They're equipped with cameras that can see many wavelengths of light, so red, green, and blue like we see with our eyes, but also things like infrared light and ultraviolet light, and measure their intensity for each meter on Kanza, or perhaps in some cases even more fine scales. The same plane is also equipped with a newer technology called LiDAR. So it uses lasers to produce 3D structures of both the Earth's surface, but also the vegetation on top of that surface. So right here is a picture of what one of these LiDAR point clouds look like, where you can actually see the 3D structure of a tree using this technology. And so we're lucky enough that starting around 2016, a National Science Foundation initiative gives us access to these types of data. So this is just a quick image of a portion of Kanza as our eye sees it from a satellite or airplane. It's the red, green, and blue wavelengths of light. You can see splotches of green down here, these darker splotches up here, which we know to be shrubs in my lab. We can also look at this to include things like infrared light. It turns out plants differ in how much infrared light they reflect or absorb. And so we can use that to find differences in vegetation as well. So these are the visible spectra of light. And this advent of this laser-based technology, LiDAR, gives us things like 3D structure or canopy height. So in the photo I'm showing you here, darker areas we've determined have a higher overall canopy of where the kind of peak of the vegetation is. So areas in green are closer to 2 or 3 meters, so that's about 7 or 8 feet tall. And areas that are really dark are upwards of 20 feet tall. And so one thing we've been doing is trying to train computers to find types of vegetation we're interested in. And a type of vegetation we're really interested in is shrubs and trees, because shrubs and trees are moving into many grasslands in this region and essentially taking them over and displacing the grasses that underpin grassland biodiversity. So what we've been doing is we gather training points using high precision GPS units and interpretation of aerial photos and categorize them into things like grassland, shrub, tree, or other things like water and roads. So right now we've generated over 200,000 different pixels on Kanza Prairie where we know what the type of vegetation they are. So we feed those into a form of machine learning. And eventually the computer actually becomes quite quite good at finding these same vegetation types for us. And so we evaluate them against another set of pixels where we know the vegetation type. And what we find is that 93% of the time, we can correctly identify the type of vegetation we're interested in. And this is a reminder that all of you have actually participated in this exercise in some way too. When you're clicking these images, they don't just want to know if you're a robot, you're actually helping train another robot to find these things. So you're giving the computer training data so it can try and figure out how to find these things in the future. Same goes with those things where you tell it what numbers you're looking at. So for instance, here's another one of these aerial red, green, blue images. This is the parking lot of Kanza Prairie. So if you've ever gone out to the nature trail and parked, this is right where you parked. And so this is how our combination of technology and training using ground-based data sees that same location. This kind of 3D texture I'm showing you is based on that LiDAR technology. So it's a hill shade layer, we call it, based on the nooks and crannies that we can see at really high resolution because of that technology. Our machine learning algorithm is what will tell you if an area is tree, so showing this gray color, shrub shown in a yellowish color, and green in for grassland, and then white for things like paths and roads. And so you can see in white, we have your parking lot here. If you're familiar with here, you walk through the trail under this tree canopy, you cross the river in white, and you know that there's a few sets of trees right here when you get in, a few cedars and a couple honey locusts right there. And you see our computer is doing a pretty good job identifying those same features. So here's a bit more complex vegetation. This is out in Kanza Prairie where we have our bison located. And so let's do the magic swipe again, and you can see the 3D structure. Areas, again, in yellow are shrubs, and we see even within the shrubby areas, there's texture there. They're not a homogeneous blob. They vary in their height within these locations. And we have these trees dotted and interspersed throughout those shrub areas. And we can also see these interesting patterns emerge between where shrubs occur and then kind of interdigitate with the grassland vegetation. And so let's just quickly look at how we can use these kind of technology to visualize the effects of bison and also quantify the effects of reintroducing this iconic megagrazer. All the images I'm showing you right here are a location where we've taken our bison away. There's no bison in these grasslands right here. The portion down here has been burned every year, and the portion here has been burned every 2 years. And what you'll notice is that, except along these rivers, these are almost purely a grassland system in the absence of bison and by burning every 1 to 2 years. Something kind of magic happens though when you go up here. So if we burn every 3 to 4 years, this is burned every 3.4 years on average, we see a massive increase in shrub cover. So a huge portion of the grassland has now been taken over, although all we did was do a small change in how often these fires occur. Similarly, if we burn every 4 years, you see that becomes a shrubland as well. And so now let's think about how the bison impact these same patterns. I'm showing you an area that does have bison present and that we burn at different fire frequencies. This portion on the right is burned every year. The portion on the left is burned every 2 years. And hopefully your eye can pick up a major difference here already. Areas burned every year have a decent amount of woody vegetation, at least compared to our areas without bison. Areas burned every 2 years, in particular, have much more shrub and tree coverage than areas without bison did. And then areas burned every 3 to 4 years, similar to the areas without bison, see a pretty substantial amount of shrubs and trees moving in and taking over our grassland system. It's a little hard to see here, but it actually is slightly less woody vegetation though, in this example with bison and burning every 4 years. So what this has been allowed us to do is, in the course of a single summer, we've been able to quantify patterns of shrub and tree expansion into tallgrass prairie over our entire site, which is something we've never been able to do before at Kanza Prairie, at least with this amount of resolution, and as far as I'm aware of. It's also allowed us to find this key relationship between fire and shrub coverage, depending on whether or not we bring our bison back. So areas without bison show this really sharp threshold where a small change in fire leads into a large change in vegetation. This is something we call a tipping point, where a small change makes a really big difference. We see though that in areas we've reintroduced our bison, the relationship's much more gradual. So they almost bring a sort of balance back to this system where they don't show these sharp tipping points anymore. And so I just want to leave you with an analogy of what I think this technology means for us in a somewhat art-based example. In the past, us ecologists, we've gone out and we recognize there's a whole large system that we're studying. So this could be a painting you're trying to restore, but we've almost never been able to restore the whole painting. We haven't been able to quantify every inch of the surface. So what we do is we quantify a subset of it and use statistics to try and generalize about it. So perhaps based on these plots here that I'm showing as areas we know information about, we could say that this is a famous Renaissance painting of an Italian woman. And we might be able to tell you even more about it, but we very rarely get you that full wall-to-wall coverage of what we're studying. Satellites that can quantify things at this kind of wall-to-wall coverage, so see the whole painting, have existed since the 1970s and 80s, and they do continue to improve, but they're much further from the ground than these airplane-based technology that we're using. So that view is complete, but pixelated. It's not as fine a resolution. And so what I think is really interesting is that now with these technologies, we're starting to get closer to a wall-to-wall understanding of our ecosystems with greater resolution. Now, we're not all the way there yet. We don't see it down to the level of detail that we would hope to, but we're getting close. And so some of my real hopes are that these approaches are going to allow us to understand environments in greater detail. We're probably going to be able to understand more of these environments because we can do it quickly. It's going to provide new ways to experience these environments visually. But I do also hope we stay connected to our on-the-ground approaches because they're what gives us context that allows us to appreciate what's behind these things. So thank you for your attention, and I'm looking forward to handing it over to you, Luke.
Thanks, Zach. Let's do my screen share. All right. Everybody see this okay? Yeah, so this looks probably familiar to many people. Lots of data, and at the sight of it, you might run away. But I think these days, being familiar with how to process data into something meaningful is a pretty important concept, especially in the sciences, but maybe not thinking about it so much in the arts is not as common, I would say. So the need for an interpreter, I think, is quite important. I wanted to show this because this is probably what most people think of when they think of visualization for data, and 2D graph, 3D graph, and that's great. I have nothing wrong with that, no qualms with that. I think they're extremely useful, but they have their limitations, right? So I think the volume of information and the way that we want to synthesize it now requires new formats to be effective, right? So what you see here is a 7D visualization, and I'll explain a little bit more about how it was created and why it was created. So the visualization you just saw was created completely with a scripting language called Python, which many of you may be familiar with, inside of a 3D modeling program called Blender. None of this was achieved, this image was achieved with any of the traditional means of modeling at all. So no handwork, this is just writing a script and pressing a button and running it, and then out the other side comes this marble-like sphere with all this data encoded into it. And why is that important? Well, with this method of visualization, you can feed this script any amount of data, and it will create this object based on any unique set of data that fits the format, and it'll allow to create an infinite number of these visualizations at any resolution. Again, that's assuming that your computer doesn't turn into a bonfire from computing too much. It also allows us to create a lot of different variations of the same type of visualization. So you can better tune the way to read it rather than using traditional means, which would take much longer. For instance, we can change the color scheme, or to show how leaf segment area is distributed over an entire plot. So a little bit about the parent project for this. One of the main goals here is finding solutions that will help society deal with food shortages that are predicted for the future, which we know is coming, and how this project aims to create mathematical models combined with observational data in order to create better predictive methods for predicting traits in crops. And then the credits here, these folks are incredible. And Dr. Welsh, who I've worked closely with and who was really the visionary for this project, and then Dr. Franklin Fonjo Fotu of Langston University, and Dr. Philip Alderman from Oklahoma State University. And there's many other people involved in this project who are incredible, but too numerous to name right now. But you all know who you are. So what information did we gather for the marble histogram project? What you see here on the left is a leaf, and it's divided into leaf segments. So those little red pieces show the normals, or which way the leaf is pointing in space. So that's two pieces of data: the angle of the leaf, the declination, and the azimuth. And then the leaf segment area, so how much area the leaf segment actually physically is, and then where that leaf position is in space, so where it is in the canopy, X, Y, and Z. And this is a simulated plot of wheat. I believe it's a meter by meter, but I might be wrong on that. And it was produced using this model created by Evers and that team with an autoregressive twist on the midrib to show the changing twist in the leaf segments. And autoregression meaning that it calculates the twist based on the previous twist in the series. And this is 10,000 leaves, which is 150,000 some odd leaf segments. And that is the data that's been gathered for this particular marble. So all of that data was summarized into 10,800 combination groups, and we reduced it down into these X, Y, Z coordinates that are mapped to radial locations, so where the segments are in space, mapped to where that the segment is in the sphere radially. The normals, so those longitude and latitude values tell you, where that segment lies in the sphere. Longitude and latitude tells you which way the leaf segment is facing. And then the transparency is proportional to the probability of all of these attributes happening. So the more that they occur, the more opaque the segment will be in the sphere. And the mean invariance of marginal distribution of the area mapped to hue and saturation. And I'll just go through them quickly so you can maybe a little bit better understand visually. So these are those latitude values are mapped to theta, or the theta and phi, so the declination and the azimuth, and that's where they fall in the marble. And that answers the question, what is the angle of the leaf segment? But it also, and mind you, I'm not a scientist, so full disclaimer, I'm an artist, and these are things that I think about when looking at and designing this type of visualization. So what can we infer from this type of thing? So I'm thinking, well, which direction does this tell me which direction the sun is, or maybe what time of day it is, or what time of year, or are there weather conditions that are obstructing the canopy and changing the way that the leaf is actually angled? So this is looking from above, at the marble from above at a cross section of it, so right in the middle of the marble. And these are those leaf segments, and where this corresponds to where they are in 3D space, so they're X, Y, Z values. And this answers the questions, where are they in the canopy? But again, what can you infer from that? And some of the questions I asked myself were, where are they, obviously, where are they, the segments in the canopy? Could you tell like the stage of growth, or how mature the canopy is, or where the growth is happening in the canopy? The mean and variance being mapped to the marginal distribution of area. So the hue being the color, and the saturation being the intensity, for an easy to understand word, intensity of the color. And that answers the question of how large is the area of each of those leaf segments, and what is the average area of the grouping of each of those leaf segments. And the marginal distribution being the subset of leaf segment area. And then finally, the transparency, or the opacity, mapping the probability of any of those combinations happening. So you see on the outer portions of this sphere that things are quite transparent. You almost can't see the sections or the segments in the sphere, because those combinations on that portion of the sphere happen so few, don't happen as often, sorry. Down here, this is a different scheme. So this kind of shows everything at full opacity, so you can get a sense of what the sphere looks like at full opacity. And here's just another view of the sphere a little bit closer up. So I have been working on a new material model, which includes 3 different types of materials. Instead of just having glass segments, we're going to have colored glass segments, water glass, and colored milk glass. Water glass is also known as sodium silicate. And I thought it'd be interesting to show you a few examples from the museum's collection that actually relate directly to those types of materials, so you get a sense of what those materials are. Many of you probably have seen this before. This is Dale Chihuly in our lobby. And this is all colored glass, this whole piece. And then water glass, or sodium silicate, these are what's called cullets. And they're used in all sorts of things like detergents and soaps, and in glass also. And it's water soluble. And it has an index of refraction that's very similar, kind of in between glass and water, which makes it kind of an interesting material. And you can see it has sort of like a mineral looking structure to it. And then colored milk glass, which is completely opaque, right? And this is another Dale Chihuly that's also from our collection. And then this is probably a combination of just about all of those things, with the colored glass, the sodium silicate, or the water glass, and then the very opaque colored milk glass. So a finished marble with those materials might look something similar to that. And this is just a quick render of what some of those materials might look like. And these are just surface renderings, so they have the properties of some subsurface scattering and sheen and clear coat and that sort of stuff, but they don't have volumetric shading yet, so they'll end up looking a lot more realistic. And this is sort of a first go fail. I thought you guys would find this kind of funny. So I also thought I would mention that this project has led to a little bit of museum advocacy here, has led to some interesting projects. We worked with Franklin Fonjo Fotu's students from Langston University. And Franklin, if you're watching, I'm sorry if I butchered your name at all. Linda Duke, our director, did a VTS session with students from Langston University to introduce some critical thinking strategies for looking at artwork, analyzing artwork. And then Dr. Welsh and I gave a lesson to the students on perspective and a little bit more advanced techniques on curvilinear perspective in order to analyze and look at some artworks a little bit more carefully, with this goal in mind, to challenge those students to create a digital companion piece to this work here, which is Kansas Wheatfield by Joe DiGiorgio, which is a very large piece. It's 20 some odd feet long by I think 6 feet tall, and is an incredible painting. And here's a little bit of detail. You can see the individual brush strokes here. So the students are charged with creating a companion piece to this that would be projected or shown on an opposite wall. And just a little bit more museum advocacy. One of the benefits working with on an EPSCoR grant, it's great because it provides a new avenue and more resources to support science researchers and students who are pursuing those ideas that have connections with arts-based research and formal visual art analysis. And why, you might ask yourself, why would scientists collaborate with art museum? Maybe not something that you'd think about, but I think the implications are pretty interesting. We can support each other in very interesting ways. You know, artists have talked about problems that are happening in current society, and scientists are doing the same thing. And we can use the museum as an avenue to create conversation between both those arts-based ideas and the science. And I think that's really interesting and important. And it can further our mission and an artist's mission and science mission. So I thought I'd boast a couple funny failures along the way, but are they failures? I don't know. I think they're kind of interesting looking. Here's just another really grainy looking, and this is actually a stereo pair. So if you're about 3 feet from your monitor, well, depending on how big your monitor is, you kind of cross your eyes. You do that thing where you cross your eyes. And then you should be able to see it kind of look like it's 3D. So I'll leave that up there for a second if you want to take a quick moment to look at it. That's it. Thanks, folks. Oh.
I think you're muted, Linda.
Yep, you're muted, Linda.
Sorry, I clicked it, but it didn't work. Thanks so much, both of you. I know I have some questions, and I see that some of our audience members have put some questions in the Q&A. But before we get to those, I just wanted to ask if you two have questions or comments for each other.
I do have a question for Zak. I wanted to ask you how you see technology, how important is technology to furthering the communication of what you're doing to the general public? Is it an integral part of what you're doing, or Is there something that's just more important than that idea?
It's important. One thing I guess I would say is there's a national trend, and it's been going on a long time, of people interacting with natural environments less and less and less. And there's a pretty robust evidence that direct interaction is one of the things that actually fosters a connection that might make someone interested in conservation of an ecosystem. So I think that will probably remain the irreplaceable portion of communication and environmental science. That being said, the impact of humans is now so global, it's going to be impossible for people to experience the majority of threatened ecosystems directly. So I think technologies that can potentially let people see what it's like to be in these systems will be very, very helpful. So for instance, one of our aspirations is to take this kind of more 3D view of Kanza and try and set it up kind of like when you do Google Earth, like Street View or something. We're very far from that, but that's like our pie in the sky, that you could drop the pin into Kanza and like have a look around. And if we are able to ever get there, I'll be super excited, and I hope that would be a helpful communication tool.
Cool.
Luke, can I ask you one question?
Absolutely.
So just how hard has it been to think in 7 dimensions? Like how long have you been working on this, and what was the first step? As soon as I get to 3, I'm pretty good at 3. I can kind of do 4, but after that, I'm frankly at a loss. And so I'm just curious how that process has been like for you.
Yeah, so to be honest with you, Dr. Welsh played a really huge role in that, because it was sort of his vision that created the idea of 7 dimensions. But trying to actually create something with that much data encoded into it has definitely been, that was definitely a huge challenge for me. Where did I start? Looking at the data, trying to understand it, and trying to understand how each component would work, and how it would work in unison. And I'd say I'm far from successful, at least what I would consider completely successful at this, because you're looking at a still image, you're only seeing it from one angle, and so you're not actually getting all of that information. So something like this, where you can look at a single image of it, but you're actually only able to infer something like a snippet of that information. And so to be able to truly interact with this thing and analyze it correctly, you'd almost need to put it in virtual space and like spin it around, or take it apart in virtual space and look at, let's say, the distribution of all of these segments together. And maybe after training your mind or training your computer on how to look at these things, then we could like actually better understand or better use them. So thinking about how to create this marvel so that people can see it in the right way, I think that's definitely the biggest hurdle. And I just sort of dug in, just started trying things with writing code and just little chunks at a time.
Can I chime in on this very topic? One thing that's really come to me over my years working in art museums, I think a lot about the word aesthetics. And that's a term that kind of carries a lot of baggage, and it means different things to different people. But everybody knows what anesthesia means. It means not being able to take in information through your senses. But aesthesia is the opposite. It is gaining information and understanding through the senses. And I think, to me, it feels like when our more linear, call them logical, ways of thinking cannot encompass a vast amount of information, like 7 dimensions or a ton of data points, sometimes our aesthetic thinking can click in and pull together maybe not a detailed understanding, but a more holistic one. And I think for me, that is the reason it makes sense for the arts and sciences to not be so separate. I think the arts have something to contribute, and I think science needs to be better understood by a wider audience. And I think some of us who work in the arts have some experience with using the senses to help people understand. So I was really fascinated in your presentation, Luke, that you're creating a situation where the viewer can be primed to know that every single visual perceptual element has meaning and is data driven. I mean, that's kind of a mind-boggling concept right there, that something as beautiful and elegant as that marble could be the container of that much information. But Zak, I was really fascinated in your presentation. You know, it occurred to me when you were showing the Mona Lisa fragments and then the different ways it could be pulled together. I feel like the visual technologies that you're using, I mean, Cartesian traditions in science, you know, where everything is experimentally derived and grounded in evidence, has resulted in us having pieces of understanding. And I think people who are concerned about environmental and ecological issues realize that what's badly needed is a more holistic comprehension. And it does seem to me like some of the visual tools you're working with, they're still data derived, but they're actually allowing us to have that more holistic view. I think that's extremely exciting.
Yeah, I mean, we've been excited for sure. I mean, the first couple of times we ran this and it started to actually work were very exciting for us for sure. To, you know, see that pop out has been very satisfying.
So cool.
In our field, a frequent metaphor is the blind man and the elephant, and the five blind. And I don't mean this as a derogatory way, but if you only can experience one component at once, and you were, you know, have the tail of an elephant or the trunk or the side, you would conclude that it's a completely different organism, and that you only, you know, understand what it is once you can actually pull all four pieces together at once, basically. So
exactly. Well, we have a few interesting comments and questions in the Q&A. Caleb Sowers writes, how much training data have you found is necessary? And I believe he's directing this to you, Zak. I recently read a paper counting the number of trees in the West African Sahara and Sahel. They needed 90,000 manually drawn tree crowns. And I imagine those are somewhat larger than the shrubs, although I'm not sure of the quality of their imagery relative to the neon stuff.
Yeah. Caleb, that's a really good question. I know the paper you're referring to is a really interesting paper. So how much data are required is just going to vary based a lot on your application. So, I mean, we're only trying to, first off, we're doing a pixel view. The study you're talking about does something a bit more sophisticated than what we're doing, which is differentiating individual trees from each other too. So for some of our pixels that are 2 meters squared, there could be 2 individual trees in there, and we don't know that. All we know is that that's a tree. And so they're trying to actually pick out each tree so they can tell the size of the trees as well as how much locations are covered by trees. So by definition, they're going to need more training data than us because they're trying to do something a bit more complicated. Also, they're covering just a much huger range of spatial variation. So, you know, we probably have about 5 to 10 common tree and shrub species on Kanza. If you cross such a large area like the Sahel, you're going to have to be able to pick out, you know, dozens more tree species. So by definition, they're going to need a lot more training data than us. So currently we're at 200,000 though training pixels for our approach. And with the pixels we have, at least we're doing a pretty, in my opinion, I think we're doing a pretty good job that the computer's, you know, quote, getting it right 93% of the time. In fact, I think sometimes it actually gets it right more often than we do at this point. It's slightly more accurate than us just as a human. We almost trust it more than ourselves at this point. So yeah, that's a great question, Caleb, and a really cool paper.
Another question, Anonymous, is it better to have a linear change in shrub cover or a tipping point?
Yeah, also a really good question. To some extent, from like a normative perspective, so just do we value this plus or minus? One actual negative impact of the bison at an annual or biannual fire frequency is that they're letting more shrubs in. So the relationship is more gradual, but at high fire frequencies, actually we do get a bit more shrubs occurring. We are starting to find that potentially at really long fire frequencies, some of the activity of these bison actually beats back the trees and shrubs a bit. So in this case, it's more, I'd say, interesting biologically that this tipping point emerges and just tells us about whether systems tend to be gradual or more binary if we take something important away, like a bison. And so that's the main answer to that question. I do want to note, though, that despite that negative impact of bison letting a bit more shrubs in, they have this massive positive impact on plant and insect biodiversity. So locations with bison, even if they let in a bit more trees and shrubs, maintain a much, much more diverse community. So yeah, great question too.
Yeah, and there's another good one for you, Zach, but I'd like to move to one that's especially directed to Luke. Anna Schatz says, great talk. I'm curious what you would envision for an exhibit of scientific ideas. Luke, what might be a scientific concept that you're really interested in conveying visually? And Zach, how might you envision a visual display of your data for a public exhibit?
Oh man, great question. Geez, I honestly, I think I'd be open to anything, but you know, our mission at the museum is regional collections, and so I think anything regional, especially since a lot of the other museums around here, at least our museums, don't really focus on regional, and that's what our focus is. So anything I think that deals with regional issues would be fantastic. So stuff that Zach's working on, or stuff that Steve's working on, you know, you name it. Things that I don't know. Yeah, anything regional, I would say. Yeah, I have a lot of interest in science, though. I will say that. Anything from physics to, you know, computer engineering and that sort of thing. So I'd be interested to hear any concept or develop anything, to be honest.
Did you want to comment on that, Zach?
Yeah, sure. Just kind of visual display of data in a public exhibit. I mean, this is kind of going back to an answer I gave before, but if we can get this into a kind of interactive format, I think that'd be really interesting, where someone can pick what area they want to zoom in on and focus on. It might also be interesting to hold back some of the information at first and just see if people can think through perhaps why some of these differences emerge, and then allow one to, like, okay, now show me how often this burned, or show me, you know, what kind of animal was there, and let people kind of interactively, you know, explore these would, I think, be very gratifying. And then to also repeat that other answer, if we can ever do this as ability to kind of plop someone on the ground, it's a very disorienting experience to do ground-based work in these really shrub encroached areas, because you're just completely surrounded by them. It's a very dense vegetation. It's a qualitatively different experience. And so if we're ever able to start communicating that, I think that would be very gratifying.
Cool. Well, and I would just throw in that this very question about the display of, you know, using technologies of the visual and using the public forum of the art museum as a kind of portal into the creative research that people are doing at K-State is something that campus CIO Gary Pratt and Dean of Libraries Laurie Getch and I have been talking about quite often lately. And I think especially with the development of Sunderland Innovation Lab, that's going to be kind of a catalyst for more student and faculty projects that use the tools that will be available in Sunderland. And I think that's ripe for partnership. There is a question here for Zak from Lee Scabland. How much of Kanza has been analyzed using the process you showed us this evening? Are the areas you showed us representative of bison and non-bison areas? What are the known and likely future differences in the amount of woody species for cattle grazed areas? Does the work you showed us change how you think about how often the prairie should be burned and when burning should occur? Wow, there's a lot of questions there.
All great questions. Hi, Lee. Lee and I are neighbors. So Lee, we've done the vegetation classification for all Kanza. So it's about a 10 mile squared area. It was a little difficult for me, but I held off on putting a data slide. I just wanted to do maps for this one, but we have done statistical analyses of pretty much all the locations that don't have bison on Kanza and all the locations with bison. So that's about 60% of the site. And so those linear versus kind of nonlinear relationships I showed you are caricatures of the statistical models we've generated to represent that relationship. And actually, I should mention we've done ground-based measurements of this as well. So we're pairing the data, the kind of big data approach, and the classic ground-based approach. So those are pretty representative. Those maps I showed you. We have not started working on our cattle units yet, though. So we do have cattle units on Kanza. The fire frequencies have shifted around a bit more, so they're a bit less consistent, but that is kind of on our to-do list. And we do know there are some areas with more versus less woody plant expansion on Kanza. We just haven't looked at that yet. And then for that last question, if this changes how often we should burn, honestly, I do think, the conventional wisdom is that these locations used to burn every 3 or 4 years, probably historically. It's looking like burning every 2 years is probably going to be more realistic for maintaining, a lack of shrubs and trees. It's due to a change in the atmosphere of the chemistry of our atmosphere and how it impacts the drought tolerance of woody plants. So I think there's larger scale changes that might be requiring us to burn more often than we think we needed to historically.
Cool.
All right, that's a lot of information. I think Eva had a similar question, and so I hope that helped Eva. We're really hoping to get around to the cattle question soon.
Oh, yes. So Eva Horn had asked, have you looked at the cattle units and do you see the same patterns? Yeah. So I just want to say this about I talked about a relationship between ITS and the library and Sunderland. We have since around 2013 and through a partnership with a number of K-State departments and including facilities grounds, and especially the leadership of landscape architecture professor Katie Kingery-Page, we did develop the meadow adjacent to the museum as a kind of native plant mini park with kind of an aim of pointing people towards Kanza, having something on campus that really reflects the native ecosystem and some of the native plants here. And I hope, Zak, as you were saying, offers an opportunity for people to have direct personal contact with an ecosystem instead of just reading about it. So that has been very important to us. There is a question from Jeffrey Sheldon. How do we break down perceived barriers which keep artists from lending their skills to data visualizations?
I can weigh in on that. That's a really good question. Yeah, I don't know if there's this idea maybe that the fine arts don't really interact with scientific research or those sorts of fields. When I was in college in fine arts, I didn't see much interaction between the fine arts and other departments really. we were just kind of like the weird kids doing, expressing themselves or what. But I think that's changing. I think that's changing a lot now, especially with there being more digital art created. I think students and young artists are now finding that working on a computer can be a completely different experience in the way that you might express not just yourself, but maybe an idea. And so hopefully that change will happen quicker and not be so gradual as it has been. But yeah, I think, fine arts teachers telling their students that there can be interaction between other fields is a really important idea. Sticking to just traditional teaching methods and ideas, I think, is a disservice to the modern day student. And so the more that happens, I think more you'll see students not worrying so much about being, a highly skilled painter, but maybe thinking about an avenue which is much different, and maybe helps to anchor them in areas of professional life that they may not have thought before, and being useful in places like data visualization. So yeah, it can be quite a journey, I think, at this point in time, but hopefully in the future it'll change.
Yes, and I don't think it's just about computer technology either. I mean, the visual arts, the word visual automatically conjures up all kinds of scientific aspects of perception. And so I think the visual arts have a long history of being taken up by people who are naturally interested in science as well. Stephanie Boints, I'm sorry if I pronounced your name wrong. How does Kanza handle an accidental / natural fire?
I am not the best person to ask about this, but we did just have actually a wildfire on Kanza. Well, wildfire in that it wasn't planned. So in general, people who manage the site quickly will try to rally around, use fire trucks and other techniques to corral the fire as quick as possible, unless there's a reason not to do so if it's an unplanned fire like we just had. So actually some of those watersheds I just showed you all just burned in an accidental wildfire over last weekend. So we're very glad that we measured them before they burned.
Interesting.
Thankfully, 3 of them were planned to be burned anyways. And then for a prescribed fire, the main technique is, say your wind is coming from the southwest, you would do a really careful burn along the northeast perimeter of that fire. And then you can light a fire in the southwestern corner, and as it moves upwards towards the location you burned, it's going to come up against an area that's largely been burned already, and you hope that it doesn't jump over that location. So that's the typical technique for a prescribed fire. I guess I'd mentioned too that to some extent, the more you burn, it's a little easier to burn, in that if these systems eventually become something like completely covered in cedar, your options kind of disappear, because that system can house an extreme fire that's very, very difficult to control. So to some extent, if you keep fuel loads to a manageable level through somewhat frequent burning, you make your job somewhat easier too.
I think California is dealing with that situation.
And we might be eventually too.
Yeah. Eileen Wong, a curator at the Beach Museum of Art, is asking you both. She says, your presentations make me wonder if we are looking at a future with a new type of artist, one who specializes in data visualization, someone who is both a trained scientist and an artist, or will artists and scientists build increasingly close relationships but remain separate? Interesting.
Yeah, it is very interesting. I think that the former exists already. It's probably not really common, but it definitely exists.
Right.
You probably see some folks maybe getting a formal education in science and then having a passion for, visualization and then doing that sort of thing, and even vice versa. I'm an example of that. And will they remain separate? I don't know. That's a good question. I think time will tell, but I think right now you're seeing some of both. Being extremely specialized, I think it depends on maybe the level at which you're making these visualizations. Maybe some of the more complex and complicated things, you would have somebody who's embedded into a team that specializes in visualization, but also has the ability to understand the content really well. So I don't know. That's a really good question.
We're getting near the end of our time together. I see that we have a couple more comments and questions from Lee and a thank you from Marty Veneer. So thanks for checking in, both of you. It looks like you're reading Lee's question right now. I'll just quickly read both of them in case you want to comment. Thanks to each of you. I'd be interested to see artists address the need for every citizen to be aware of human ecological interrelationships. For example, the impacts of planting invasive species and the various costs of then trying to manage the degraded landscapes, or the connection between how we develop cities and produce crops and water quality, aquatic habitat degradation, and flooding. So again, back to this holistic picture that perhaps artists and scientists could join forces to convey to a wide audience.
Yeah, absolutely. I would be very interested to see that also, and I think that to some extent is happening. We've had a few shows that address some of those issues. Maybe not the exact issues that you're talking about, but yeah, we've definitely tried to be part of that conversation.
For example, the Ogallala Aquifer, we had an artist who was very, very interested in that and had been researching those issues, and they informed her images. Yes.
Exactly.
Well, I don't know if anybody has a final comment, but this has been such an interesting conversation, and I'm grateful to both of you.
My comment is just thanks for providing this platform, Linda, and all you folks at the Art Museum. Enjoyed
Our pleasure. We are really pleased.
Yeah, Zach, thanks for participating with us. We really appreciate it.
Absolutely.
We loved hearing what you have to say. It's great.
Yeah. Yeah.
Thank you both. Have a good evening, everyone.
Thanks everybody for coming.
I think everyone.